Let's do an example of a definite integral, which requires integration by parts. And the way we'll proceed doing this problem is exactly the same as an indefinite integral. All right, we're going to compute the definite integral from 0 to 1 of s squared e to the s ds. And you can recognize this as integration by parts because you've got the product of two functions, s squared and e to the s, and I don't see any way to use substitution to simplify things. So as I said, we want to do this the same way we do integration by parts for indefinite integrals, and in fact what I will do is simply write it as an indefinite integral first. I'll find its general antiderivative, and then I will convert it back into the definite integral at the very end of the problem. So I'll need to identify my u and my dv. And looking at this, I see a very nice u, because s squared gets simpler when you differentiate it. A nice dv, because e to the s ds does not get worse when you anti-differentiate it. So let's put all that together. So I said I wanted my my u to be s squared. I want my dv to be e to the s ds. And then, what does that give me for du? Well, I'll take the derivative of s squared to get 2s ds. And then I'll anti-differentiate e to the s, which is its own derivative and integral. And now I can plug it all in to the formula, u times v minus v du. Now, notice that we do not have a nice integral that we can just anti-differentiate directly. That's fine. We're going to do this one more step. We're going to identify a new u and a new v. And in this case, I think I should just keep going. The 2s can be my u, and then the e to the s ds can stay my dv. And I choose it like this because when I take the derivative of u to get du, that's just 2 ds, and that's simpler. We want things to get simpler with each step. Likewise, my dv is e to the s ds, and while that won't get simpler, it doesn't get any worse at least, that gives me a v of e to the s again. So let's put that together. S squared e to the s minus, and we'll be careful to put brackets around the second step of integration by parts so we don't make any mistakes. I need u times v, 2s times v e to the s minus the integral of v du, and that's e to the s times 2 ds. And then once we've done that step, we can distribute the negative here to get negative and positive. And finally, this last integral is something we can integrate directly because it's just a constant multiple of 2, so it can just come down. So my general antiderivative is s squared e to the s plus a negative 2s e to the s plus the integral of 2 times e to the s, that's just itself, 2 times e to the s plus c. So that was my general antiderivative of s squared e to the s ds. But that wasn't the problem I was asked. My problem asked the definite integral from 0 to 1. So to make my life easier, I just did the indefinite integral. And then at this very last step, I will rewrite it as the integral from 0 to 1, s squared e to the s ds. And then I can just put big brackets around the entire antiderivative using the fundamental theorem of calculus here. And evaluate that from s is equal to 0 to s is equal to 1. I don't have to do any change of variables unlike substitution because I just kept my solution in terms of the original variable s. So now it's just a matter of plugging in the top minus the bottom. If I plug in a 1, it gets me 1 e to the 1 minus 2 e to the 1 plus 2 e to the 1 minus, plug in 0, I get 0 e to the 0 minus 0 e to the 0 plus, you have to be careful here, that's 2 e to the 0, so that gives me a minus 2. And then notice that, well, it seems 2 e to the 1, negative 2 e to the 1, those cancel. I'm left with e, 1 e to the 1 is just e, minus positive 2. And that's my final answer.